Hey there, how's it going? Terry Brown, Mechanical Engineering here to go through another engineering mechanics problem. Let's have a look at what it is. So this problem would be categorized as a frames and machines problem. So you may have that chapter in your engineering mechanics textbook and in Hibbeler and Hibbeler, which is the one I've taken this problem from. It's in the chapter on structural analysis, and the last section after he's looked at trusses, he has this section on frames and machines. And for mechanical engineers, I think this is probably the most important topic in the book for being able to analyze any real frame, machine, mechanism that you come across. Right, so this problem is a machine. Now, whether you can distinguish between a frame and a machine doesn't really matter. But in general, a machine will be used to transmit a force through the mechanism or machine and convert it to a force in some other direction, and maybe there'll be a mechanical advantage through the mechanism or machine, and so on. So, and the other thing that categorizes a machine as opposed to a frame is the fact that the members can move relative to each other. All right, so let's start to work through the problem. All right, so let's have a think about how we might solve the problem. You should know by now the method for, or the process for solving equilibrium problems. In these particular frames and machines problems, we firstly need, we don't have to do this first, we can do this a little bit later, but I've written it first here. Identify two force members. And then the next, in this particular problem, we need to calculate the spring force. But for equilibrium problems in general, where we're trying to analyze forces and or moments acting on a body, we need to draw free body diagrams. Now, one of the things that students find difficult about these kinds of problems, and I'm not sure whether you look at this and think, oh my goodness, what am I going to do here? Where am I going to start? And as I say, just start somewhere, but we'll have a look at that as we go on. But yeah, the difficulty is, what do I draw a free body diagram of? There's 1, 2, 3 main components here. Do I draw a free body diagram of the whole thing? Do I draw a free body diagram of the lever? Do I draw a free body diagram of the link? And depending on what you choose, how quickly you get to the answer, will be affected. But it shouldn't affect the answer that you get, right? So you can do all sorts of different things. And in fact, in this video, I'll go through 2 or 3 different ways of solving this problem, starting with different free body diagrams, just to show that you don't need to get stressed out by trying to work out, where do I start? Just start, right? But the main thing is to make sure that you properly apply the fundamentals of rigid body equilibrium and also Newton's third law, which we'll talk about as we go through. And I've just got that as my next point, because what we have to do is to sometimes separate the mechanism out into individual free body diagrams. And when we do that, so if we separate, or imagine that we separate link BD here from link CDE at point D, we've got forces of interaction between those two parts. And at that location, right, we need to obey Newton's third law of action-reaction. Right, and then once we've drawn our free body diagrams, making sure to obey Newton's third law, we can now write and solve equations of equilibrium. So as we discussed up here, what we want to do to make our solution a little bit easier is to identify two force members in equilibrium. Now, we don't have to do this, but it makes the solution a whole lot quicker. It reduces the number of equilibrium equations that we need to write. So link BD here is a two force member in equilibrium because it's got connections only at 2 locations and no other forces applied, assuming that the weight of the link itself is negligible compared to the other forces. Right, so this is a 2 force member in equilibrium. So what that does for us is to tell us the direction of the reaction force here at B. Right, so if we draw a free body diagram of this link BD, we'll see that the force at B must be along the line joining B to D, and the force at D must be equal and opposite that also along the line D to B. So if you don't remember your two force members, go back and revise that. So next thing we want to do is to calculate the spring force. Now the reason we want to do this now is because this is our only input force into the problem. Right? So we're told that we need to work out this force here, P. So the only way we can work out an actual force to use in our calculations is to work out the force that's generated by the spring here, by the compression of the spring. So hopefully you remember your spring equation. The force in the spring is equal to the stiffness of the spring times its change in length. So the stiffness was given as 6 kilonewtons per meter. So I've just converted that into newtons per meter. So 6,000 newtons per meter times the amount that the spring is compressed. So we were told that that is 0.025 meters or 25 millimeters. Do the maths and we get 150 newtons for the spring force. So the spring is compressed. So therefore, hopefully we can see that this spring is now going to push downwards on this lever. So when we draw our free body diagram, we can include that force in the free body diagram. So in this solution, I'm going to start by drawing a free body diagram of the whole machine or mechanism. Okay, and if you're not sure, that's not a bad thing to do. All right. So the other thing I like to do when dealing with these types of problems is to think from a design point of view, rather than the point of view of it's a quiz or an exam and you just need to find the quickest way to solve the problem. Okay, so that's not a very good way to think about these problems, in my opinion. The best way is to think, right, I have to analyze this thing completely, or I may even need to design the sizes of the links and the pins. So if you're going to do that, then you need to know the forces on all of the joints, on all of the members. So, if you end up, calculating reaction forces at A and B or forces at C before you calculate the force here at P, well, it doesn't really matter. You're going to need to know those anyway. Okay, so drawing my free body diagram, draw the whole component, or the whole machine rather. Make your drawings large, neat and clear. It's especially important for these frames and machines type problems that you do draw your diagrams large, neat and clear. And when you put your dimensions on, make them meaningful. Right? The witness lines are meant to be going to the points that they're referencing, so draw them there. Don't put them up here. Don't draw your dimensions only going part way between the witness lines. Take the time to do a proper professional presentation of your solution. All right, so we've drawn the free body of the whole mechanism. So usually the best place to start when adding on the forces is to start with your known load. So as we discussed before, our known input into the problem is the force applied by the spring. So that was 150 newtons pushing downwards. Next, we'll start looking at the other things that we've got applied to the mechanism. So at the top of the link E here, we've got our applied force P that's applied through the cable. And then we've got down at the bottom here our connections at A and B. Okay, so the next thing to do is to look at the supports at A and B. And if we look at B here, because we've identified BD as a two-force member in equilibrium, we know that this force will be directed along the line joining B to D. And you should know, hopefully, that it doesn't matter what the shape of this component is. Could be shaped like this blue curved link that I put here instead. The fact that this is curved and not straight between B and D doesn't matter. Right? It would still have a reaction force at B here directed along the line joining B to D. And I've got on here now the arrowhead indicating its sense. How did I work that out? If I imagine I take moments about point A down here, then I can see that the force up here, P, is tending to rotate around clockwise about point A. So therefore, our force down here must be pushing back upwards to give us a moment around this way, around anti-clockwise about point A, for equilibrium to occur. Also, our force out here is tending to cause a clockwise rotation. So further evidence that this needs to be pushing up to the left to give us an anti-clockwise rotation for equilibrium. Okay, now let's go and look at forces at the support at A. So we'll need two forces, two components of the resultant force here, or you could put a force in an unknown direction, but generally what we do is to find the components horizontal and vertical at a location like this. Right, so you can look at the other forces that are acting and try and work out whether they should be up or down or to the right or to the left. We've got quite a few forces acting here, so if we've got a force to the right here and a force to the left here, we're not sure whether this should be to the right or to the left, and so on. So you can just assume the sense of those forces, and if you get them wrong, then they'll come out negative in your final answers. Right. Give them some labels so you can refer to those in your equations of equilibrium. Right, so if we now start to take moments about somewhere to try and solve for some of our unknowns, the thing to note here is that we've actually got 4 unknowns. So P is an unknown, that's what we're trying to find in the problem. RB is an unknown, and our 2 reaction forces at A are also unknown. So we've got 4 unknowns, so we're not going to be able to calculate everything from just this one free body diagram and the 3 equations of equilibrium that relate to this one free body diagram. Right, so we're going to have to write some equations that relate our unknown things together. So P is what we're trying to find. So let's write an equation that has P in it. If we take moments about A here, we'll get an equation that relates P to RB. So down here, here's my equilibrium equation, indicating that I'm taking moments about point A by writing the subscript A here, and then I can start working through the moments of each force. So start with the force P up the top here. Its perpendicular distance from A, this is perpendicular distance up to its line of action. So that will be 0.2 plus 0.2 plus 0.15, which is 0.55. And as we discussed before, it's tending to rotate clockwise, so therefore it will be negative. So next, looking at the spring force out on the end here, we have 150 newtons times its perpendicular distance, 0.2 plus 0.8 equals 1, so put in 1 here. So even though the number that we're putting in here is 1, and it doesn't change to the 150, get into the habit of actually putting in this distance that we're using, just so it's easy for the person reading your work to see what's going on in your solution. Right, so this is also negative, as we discussed before, tending to cause a clockwise rotation about point A. And then we've got our force here at B. So the horizontal component will pass through point A, so we don't need to worry about that. The vertical component of RB will be up here. So this angle here is 30 degrees, and the component on this side is the adjacent side to the 30 degrees. So therefore we have RB cos 30, and we now need to work out the perpendicular distance from A to the line of action of that force. Right, so that's 0.2 plus this distance in here that we don't yet know. So we're going to have to do a little bit of trigonometry to work that out. So I've got 0.2 plus 0.4, and we're going, so 0.4 is this distance up here, so we need to do a little bit of trigonometry. So remembering that tan theta equals opposite over adjacent, and we have a little triangle here. Right, so we know the vertical distance here, 0.4, and we need to know this distance here. Right, so for this 30 degrees angle here, this is the opposite side, and this is the adjacent side to that angle. So for tan theta equals opposite over adjacent, we want the opposite side. So we just got to put A around here, or the adjacent side around here. So we just need 0.4 tan 30 degrees to give us the length of this side here. Okay, so we just put that in. And as we discussed before, that's going to tend to rotate anti-clockwise around point A, so that's a positive moment. And that's all we need to include in our equation now. Nothing else is causing a moment about point A. So we can make that equal to 0 and rearrange the equation to get our unknown force P that we're trying to calculate as a function of RB that we don't know yet. So we're going to have to draw another free body diagram in order to get that force. Okay, because, as I said, we have 4 unknowns in our problem. So moving on to the next page, I've just copied our diagram across to refer to. We need to think about what to draw a free body diagram of next. All right, so far we've drawn a free body diagram of the whole thing. So we could draw just a free body diagram of BD, but that's probably not going to help us very much apart from as a intermediate step. In fact, I might just do that now while I'm thinking about it, just to explain what's going to come up next in my solution. So if I draw a free body diagram of that link, then on the previous page, we worked out that we had a force acting like that at B. So for that link to be in equilibrium, then we need equal and opposite over there at point D. So this was RB and this is RD, then of course RD needs to be equal to RB, right? And then acting on this vertical member, CDE, will be equal and opposite of RD. Right? So that explains my choice here of deciding to draw a free body diagram of the link CDE. Right? So if we do that, draw our free body diagram, put on our dimensions for reference, make it nice and neat and clear so it's easy to see what you're doing. Put on our known loads, so we've got our applied force through the cable here at E, that is P. And then at D here, as I just explained, we've got the force that is applied by the link BD to the link CDE. Okay, and that's going to be equal and opposite to what I've drawn over here. And that refers to Newton's third law that I was talking about before, right? So this force here acting on the link DB and this force here acting on the link CDE, these two forces are action-reaction pairs. Okay, so what I've shown here is the force that the link DB exerts on the link CDE, and over here I'm showing the force that the link CDE exerts on the link DB. So these, for Newton's third law, action must be equal and opposite to the reaction. These things must be shown equal and opposite to each other on their respective free body diagrams. Okay, so label that, and then at C, again we've got a pin connection, so an unknown force in an unknown direction, or more usually in our solution, 2 unknown reaction components, and we put them horizontal and vertical as usual. Doesn't have to be, but usually they are at point C here. Since this is the first time that we've drawn the forces at point C, doesn't really matter which direction we put them, but let's have a look at our link here and see if we can work it out. So if we take moments about point D, for example, then we can see that the force at C needs to be going to the right to counteract the force at E also going to the right. So P up here will cause a clockwise rotation, so we need C down here, or the force at C down here, to cause an anti-clockwise rotation. And then looking at our forces in the vertical direction, we can see RD is acting upwards. So therefore, this one needs to be acting downwards. Now, as I said, since this is the first time we've drawn the forces at sea, doesn't matter if you get them the wrong sense here, you'll just get a negative value. But what you need to make sure you do throughout the rest of your solution is to be consistent. So if we draw a free body diagram of ACF, for example, then you need to obey Newton's third law and draw equal and opposite to what we have here on CDE when on the free body diagram of ACF. Okay? And if you do get a negative answer, never ever go back and change the arrows on your free body diagram. That just leads to a mess. Right? You've got to then go back and change all your equations, and it leads to more problems than it fixes. Right? So just leave them as they are. Draw your free body diagrams following Newton's third law, and then when you substitute a value that you found here into equations of equilibrium on a free body diagram of ACF, for example, you write the equation according to the arrows that are drawn, and then if you happen to have found that one of these were negative, then you just substitute in the negative value, and that will take care of the signs. Trying to do anything else just leads to a mess, right? And you won't get it right. Okay, right, so let's move on with this. So label our reactions RCX and RCY, so we can put those in our equation. So we'll start with sum of the moments about C, because we want a relationship between, or an equation between P and RD, which we know is equal to RB, which we've already calculated previously. So going through that, so the vertical component we don't need from RD, we just need the horizontal one. So looking at our angle here, so we've got 30 degrees between the force RD and the vertical direction. So the horizontal component will be the opposite to the 30 degrees, so therefore sine 30, and the distance, perpendicular distance of that force here that will be acting horizontal to the left at D, its perpendicular distance is 0.2 and will tend to cause an anti-clockwise rotation. So then now looking at the moment that the force P generates, perpendicular distance 0.15 plus 0.2 is 0.35, tending to rotate clockwise, so therefore negative, and all of that's equal to 0. So rearranging that, doing some algebra, we get the RD is equal to 3.5p. And from our previous free body diagram, we had that relationship between P and RB, and as we've just discussed up here about the two-force member, right, RD is equal to RB. So we can set RB here equal to 3.5p, right, from what we had here. So RD equals 3.5p. So now we can say RB is also equal to 3.5p and substitute this into here to solve for our unknown force P. Okay, so just putting that in to the equation and then doing the maths, we get 198.3 newtons. So the force required in the cable up here to generate 25 mils of compression in the spring is 198 newtons. Okay, so in the following pages, I'm going to go through some alternate solutions just to show you that there's more than one way to solve the problem. It shows that you don't need to know any tricks if you're thinking about the problem as a design problem, not thinking about it as how quickly can I solve this quiz or exam problem, and all you're wanting to know is the force at P. For a real design problem, you want to know the forces anywhere. So it doesn't really matter where you start. If you solve the problem by diligently applying the fundamentals of rigid body mechanics and your equations of equilibrium and obeying Newton's third law when you draw free body diagrams of components that were connected in the thing that you're analysing. In order to analyse them, you have to imagine them disconnected. when you draw the free body diagrams of those, that you make sure that you follow Newton's third law. All right, so let's have a look at my first alternate solution. So I'm just going to quickly, this is just a repeat of what we did before until here. So now I've got to the point where, right, I need to draw a free body diagram. I can't just write equations of equilibrium and try and solve with this thing. It just doesn't work, right? You can't do it. Right? You've got to draw some free body diagrams. Right, so I've said here, draw free body diagrams of the lever ACF, right, which is a reasonable thing to do. So often, if you're reading the textbook, they'll tell you, or people might tell you, just start where the known force is applied and draw a free body diagram of that. So drawing a free body diagram of the lever ACF is a reasonable thing to do. And also, right, we've got, it's not a known load here at P, but it's something that we're trying to find. So you might also think to draw a free body diagram of the link CDE, which is also a reasonable thing to do. Right, so I've started by drawing the free body diagram of the lever ACF. So if we put on our force over at where the spring is, 150 newtons, and then I've gone, and instead of looking at that, I've said, let's have a look at link CDE. And I've got my input force here, P, that we're trying to find. So then I've said, okay, as before, link DB is a two-force member in equilibrium, so I know the direction of that force, and I can work out the sense of the force by imagining that I'm taking moments about point C. So I can see the P force here tending to rotate clockwise, so this one has to cause an anti-clockwise rotation. And then at C, we've got our reaction components where we've connected the link CDE to the lever ACF. Okay, so you go through the process that I went through before to work out the sense of those. All right, so I've labelled those RCX and RCY. Now is where we need to be careful about how we apply Newton's third law. Okay, so what we have shown on the member ACF here, these forces here must be equal and opposite to the forces down on CDE at point C. Right, so having drawn these or determined these forces and their sense the first time, from then on, I have to obey Newton's third law. So up here, they're RCX and RCY. So the vertical force here must be upwards because the force down here on CDE is downwards. And then the force on ACF at C is to the left because the force down here on CDE is to the right. Okay, so what we have here are action-reaction pairs. So you know that Newton's third law is every action has an equal and opposite reaction. So here we have action-reaction pairs between the two members of this mechanism. So what we're seeing down here on the link CDE, so these forces down here are the forces that the lever generates on the link CDE. Whereas up here on the lever, we're seeing the forces that the link CDE exerts on this lever ACF. Right? So they must be drawn equal and opposite. As I said, if you get a negative value for the force in one of your equations of equilibrium, then when you're using the force in the next free body diagram and equation of equilibrium, just substitute in the negative value. Right? After you've written the equation of equilibrium according to what you've drawn on your free body diagram. Okay, so then at A, we can do the same thing. This is a new solution, but I've just kept it the same as the previous one. I won't go through all that again, but you need to label them. And now we need to start thinking about writing equations of equilibrium. All right, so here I've said, okay, I can write an equation that relates P to RD here. So from the free body diagram of the link EDC, taking moments about point C, I can do RDC sine 30 times 0.2. I'm not going to go through this slowly. I did that previously, but we end up with that equation and we get the same relationship between RD and the force P that we got before. All right, let's go on to the next page. So I've just copied across what I did previously. So looking further at our free body diagram of EDC, if I sum the forces in the horizontal direction, right, I have RCX plus P minus the horizontal component of RD, which will be RD sine 30. And rearrange that, and I get an expression for RCX. But at the moment, I haven't calculated RD or I haven't calculated RD or P. I've got a relationship between them, so I could substitute in here. So here I've substituted for RD into this equation to get RCX as a function of the unknown force P. And then looking at some of the forces in the vertical direction equals 0. We've only got 2. So we've got the vertical component of RD, which will be RD cos 30 minus RCY. RCY equals RD cos 30. And substituting again for RD equals 3.5P, I get another equation with our unknown force P in it. So now if I redraw, so you don't have to redraw the free body diagram. You know, I've just put it here again because I don't want to flip backwards and forwards to the previous page. So from our free body diagram of the lever ACF, we can take moments about point A. So now we'll have RCY times 0.2, so its perpendicular distance here is 0.2, tending to rotate anti-clockwise, so that's a positive moment. Then we have RCX times 0.2, so its perpendicular distance is this one in here, tending to rotate anti-clockwise, so it's also positive. And then we have our force out on the end here from our compressed spring times perpendicular distance, which is right, point here out to here, which is 1 meter, tending to rotate around clockwise. So therefore a negative moment, all equal to 0. So now if I substitute in from what we calculated up here, so we've got RCX is 0.75P and RCY is 3.031P. So I've just substituted those into my equation. So now I'm left with one equation with one unknown, which is the force P that we're trying to work out. So do the algebra and I get P required equals 198 newtons. Okay, so different free body diagrams, different set of equations of equilibrium, but diligently, carefully applying the equations of equilibrium, the engineering mechanics process, drawing good, neat, clear free body diagrams enables me to find the right answer and also gives me a check on my calculations that I did previously. All right, so let's have a look at another approach. So in the previous page, I found the forces RCX and RCY by drawing a free body diagram of the lever ACF. Let's have a look at an alternative to doing that. So this time I'm going to draw a free body diagram of ACF and CDE still connected. All right. So let's have a look at what that looks like. All right, so you can see there I've drawn my free body diagram. CDE and ACF are still connected. So now I have support reactions to put here at A, force at D from the link DB, and our applied force at E. So I put that in first. We know that the force at D here acts along the line DB. And so I won't go in through that again. We've done that before. And I've just kept the same RAX and RAY at A to be consistent with what I had before. So now, if we take moments about point A, right, we can hopefully you can again see that we're going to get an equation that relates RD and P. Right, so doing that, so we have P times 0.55. We've seen that before. Going clockwise, so negative. Then we have the 150 Newton force out here about point A times 1, that's negative also. And then we have the components of our force RD here. So this time we'll need both the vertical and the horizontal components of the force, because both of them are away, or because both of their lines of action don't pass through point A. So there'll be a perpendicular distance between the vertical component of RD, which will be 0.2, and there'll be vertical distance between the horizontal component, which will be 0.4. So hopefully you can see here that I've calculated the horizontal component. So here's our force. The horizontal component is this side of the triangle, which is opposite to 30 degrees, so therefore sine 30. Okay, so that force will be tending to act towards the left, so tending to cause an anti-clockwise rotation, so positive. And then we have the vertical component of RD, the vertical component here. Its perpendicular distance is 0.2, tending to rotate anti-clockwise about point A, so it's positive as well. No other forces causing moments, so that's all equal to 0. All right, so rearrange all of that, but before we do, just remember that from our free body diagram of EDC, we had that RD is equal to 3.5p. So we can substitute 3.5p into here where we have RD. Right, so let's put that in and rearrange the equation. All right, so where we had RD here, I've just taken that outside the brackets, and that's 3.5p. Rearrange all of that, and we get P is equal to 198.4 newtons. Whoops. Okay, same as what we had before. All right, so I've got another one, another solution. So drawing separate free body diagrams of ACF and CDE from the free body diagram of ACF. Okay, so starting with moments about A, RCY times 0.2 plus RCX times 0.2 minus F times 1. Okay, so we went through this before, but I'm just going to go, it's kind of similar to what we did before, but just showing you that it doesn't matter which order you do things and whether you get mixed up a little bit. Right? With this solution, I just end up having to do a lot of substitution of equations. Right? Okay, so next looking at the free body diagram of CDE, some of the moments about D this time. So here I'm doing something a little bit different, right? Because after doing my free body diagram of ACF, I can see I've got an equation that relates RCY and RCX to my input force. And if I look down here, starting with a free body diagram of CDE, I don't have any known values yet. Okay, but I can see up here I've got a relationship between RCY and RCX. So if I do an equation, equilibrium that gives me one of those values, then I'm making progress. So if I take moments about D, I'll get an equation that relates RCX to P. So taking anti-clockwise is positive as usual. I have RCX here times 0.2, tending to rotate anti-clockwise about point D. Right, so see again how important it is that you have this letter here on your moment equation. Right, without this, you have to guess what the person's doing in their solution. Right, so and if you've got to guess what you're doing, then you haven't done a complete solution. All right, so we dealt with RCX times 0.2. Then we look at P times 0.15, perpendicular distance to D, tending to rotate clockwise, so that's negative. Everything else passes through point D, so we don't need to include any of those in our equation. So put that all equal to 0, and we end up with an equation that relates RCX to P. So thinking ahead to what I'm trying to do, right? So I can now think, oh, right, P is what I'm, right, the unknown force P is what I'm eventually trying to get to. So I could substitute this value into here, and I'm getting a little bit closer, right? I know F is 150, so I'm getting a little bit closer to my solution. Right, if I now do sum of the forces in the x direction equals 0, P minus, so P up here minus RD sine theta plus RCX equals 0, I get RD equals this equation. Right, so I've got RCX as a function of P, so I could substitute that into there. So I do that. So that's what's happened here. I've just substituted RCX into here. Right, so I have an equation now that relates RD to P, but as yet I don't know RD in this solution. So if we do sum of the forces in the vertical direction equals 0, right, remember, so it's important to have in your solution which free body diagram the equation of equilibrium that you're looking at belongs to. Right? So here, these equations belong to free body diagram of CDE. Right? So we've only got two vertical forces, RCY and the vertical component of RD. So rearrange that. Substituting again for, right, I've substituted from here into this equation. Right? So we can see this P outside 1 over P outside of 1 plus 0.15 over 0.2, etc. Right, so this is now in here. I've just said here, so this has become, right, so I know that sine 30 over cos 30 is tan theta, so that's where that's come from. So now, I've got a whole bunch of equations. Right? So I can see that they're related somehow. So I've just started to label or number all of these equations so I can refer to them. If I go and look through here, so if I substitute RCX, so I've got now RCX as a function of P, RCY as a function of P, and nothing else. So if I substitute 4 and 2 into 1, then I will have an equation that has only my unknown force P in it and the input force 150 for F here. Right, so I will be able to solve for my unknown force P. Right, so just repeating that over there, RCX equals P outside of 0.15 over 0.2, and RCY equals this. So this is just repeated on my next page. Substitute all of that into 1, and we get that. So now you can see the final equation that I need to solve for P. Rearrange all that, and I get P equals 198. Right, so this solution, looks a bit more complicated, and this is more like what I see in a lot of student solutions. But the reason I've shown you this solution, that it's a bit roundabout and not as elegant and straightforward as the previous ones, is that even if you kind of lose your way a little bit, it doesn't matter. Don't panic. In a quiz or an exam, you're time limited and you do panic. But as I said, I try to think about these problems from a design perspective rather than from solve it as quickly as you can in a quiz or exam perspective. Right? So you can take your time, apply the process of engineering mechanics slowly, diligently, in a disciplined way, draw good free body diagrams, label everything properly, draw your dimensions properly, make sure you follow Newton's third law when you're drawing forces that occur or appear on two separate free body diagrams, and you'll get to the right answer in the end. Okay? And if you happen to find other things along the way, that's great. I mean, on my next page here, or even on this page, right? I've started to now put in the values for the other things that I need to find. So if this really was a design problem, right, I need to know these values anyway. Right, so I'm now calculating the magnitudes of all the other forces. Okay, so I'm not sure if I've done this on the next page or not. So now, having drawn the free body diagram of the lever before, and including those unknown forces RAX and RAY, we've got those there available for us to put the values in and solve for those unknown values that we need to design this problem. So from some of the forces, we can get RAX. From some of the forces vertically, we can get RAY. All right, so that's the end of that problem, done multiple ways. My voice just held up through all of that. Hopefully that was helpful and instructive and interesting to see how to solve a more realistic, complex frames and machines problem. So if you can do problems like that, you can solve almost any machine, mechanism, frame type problem. Okay, and solve practical engineering problems, not just the simple or the relatively simple quiz textbook style problems. All right, bye for now. I need to give my voice a rest. Catch you in the next video.